Hello. As we have seen previously, the main objective of this course and the main objective of the density functional theory is to evaluate observables. We won't care about the many-body wave function, but rather we'll put our effort in evaluating some observables. So before going on to see how we can actually get them, it is worthwhile to mention what kind of observables we are talking about. First of all, we have to focus a little bit on some specific problems. In fact, as we will see in the following, the density functional concepts are so general that today many domains in science benefit from DFT applications, from physics to biochemistry, from superconductivity to stellar materials. We cannot, in this course, speak about everything. As I said, DFT is very general, so the basic concepts will be valid in any domain. However, in order to give specific examples, we will focus on the electronic problem, which is already, we've seen that, a formidable problem. So for our many-body problem of the electronic structure, what are the typical observables we are interested in? A first example can be the equilibrium position of the atoms in a molecule. What is the equilibrium distance for these two atoms to form a diatomic molecule? This is a typical energy minimization problem that gives, via the evaluation of the total energy of the system as a function of the distance r, the equilibrium position r0. The energy minimization can give also the full geometry of a molecule, in particular the angles, like here for the case of carbon dioxide. You see how the energy minimization predicts a linear molecule with a flat angle between the two oxygens. This procedure works really well and predicts, for instance, a specific angle between the hydrogens in the water molecule. No matter from where you start your simulation, the final result would give the same specific angle, which is not 180 degrees. As well as ammonia is not a planar molecule, for it minimizes the energy with this bowl-like shape. Also, the crystal structure can be determined in this way, for instance, by evaluating the forces acting on each atom of the system. This is important for the crystal structure. But with the same idea, we can compute the lattice vibrations that give rise to phonons, like in this case. Or this one, which is clearly a different collective mode. Or, in a more macroscopic approach, we can study the bulk modulus, that is the ability of a material to resist to a certain external pressure. So these are only examples of typical observables that we can tackle in density functional theory. But they are also a specific set of examples. In fact, in all the situations I just mentioned, the main issue was to evaluate the ground state energy that, via a minimization procedure, gives info about the structure of a system and about many other quantities. But what about other observables that are not necessarily related to the minimization of the electronic total energy? Well, this is something less obvious, but strictly speaking, and we will see that, even the excited states of a system are observables of DFT. The same can be said for certain linear response functions that lead to optical absorption or electron energy loss. We will see that even if in practice we do not use DFT to tackle this kind of spectra, they are nonetheless observables of density functional, at least in principle. And this without even considering special cases like spin systems or superconductivity. Anyway, we have to go on if we want to know how to actually evaluate these observables in DFT. So goodbye for the moment. Don't miss the next lectures.